Hi, I would like to welcome you to my tutorial about arrays within the brand new graph node programming system and the new RealFlow version. So arrays is a very important concept within the graph nodes, and I would like to quickly describe the concept of arrays. If you're coming from a programming language like C++ or Python, you probably know that. So very quickly, array basically is a container or a list containing a bunch of elements or objects. Very general, these objects can be just numbers or some RealFlow nodes, objects within the scene or emitters within the scene. And yeah, there are mainly three kind of sizes which can be distinguished, like an empty array is of size 0, and array of size 1 is kind of special because it just contains one element and can be used just as a single element, like a standard number in a programming language, for example. And finally, arrays with sizes bigger than 1 contains several elements. It's important to note that within the graph node programming system, every data type is an array. So you don't have to distinguish, is it an empty array, is there one element within the array, or there are several elements. They all can be handled the same, so we think that that makes programming within graph nodes much more easier. And the main benefit of using arrays is that they can be quite beneficial multi-threaded, and so they're kind of fast within the graph node system. To take benefit of the full performance boost you can get with graph nodes, it's important to slightly change your thinking if you come from a programming language. In programming languages like Python, for example, you normally think in loops or conditions like if conditions, for loops. You can use these paradigms in graph nodes as well, but if you slightly change your thinking how to use that and use arrays and masks for the same tasks, then you can take benefit of the full performance boost within the graph nodes. I think I just get started and demonstrate some example of how to use arrays and how to get rid of loops and conditions to get that performance boost. So let's switch to the simulation flow menu. I go here to the frames post and add a graph. So maybe we start with a very simple example, how to access arrays and how to print them out for debugging purposes, for example. So pressing tab brings us to the menu. I use the array num range node. This node creates an array in the range from start to end with a given step size. So let's say we take two real numbers and create an array from the value 0, which you can see here, to, let's say, 2. And we choose like 11 steps. So if I connect that node now to an evaluator and press play here, upper bar, nothing's happened because we create an array and do nothing basically with it. But I would like to point out some special informations. If we right click on the pin here, we get a real, that's the content of the array. So this array contains a real number and it's size of 11. This number in the brackets always indicates the size of the array. If I do the same, for example, here in the input real, we see a size of 1. So this node here only contains one element, and this node creates an array out of reals with a size of 11. So let's print out the array to see if everything's working all right. I use the message print node here, and to print out an array, it's important to convert the list of numbers into a string, and we can do exactly that with a real to string node. This takes the incoming real array and creates a message. So let me change the message window to the top And if I now press play in the graph node, we see here a message print counting from 0 to 2 with 11 steps. This is one way to print out the array. Another approach would be to gather a certain number at a certain place within the array. And for that, we got the getArray num element node. The num, by the way, always stands for numerical elements. So if we work on numbers, we always can use the shortcut num to get nodes working on that. So this will return us the array at position, let's say 5. The first index always starts with 0, according to C++ conventions, for example. And let's disconnect this one, remove the guy over there, and connect that to the message print. So if I press play now, I would expect the printing of the array element at position 5, which you can see here. I would like to demonstrate how to use the for loop to print within the for loop the whole bunch of array elements. As you might know, for loops only can be contained within the compound. So I create a compound for these selected nodes, get into the compound, and add a for loop. It's basically here. And I connect this for loop to the index of the getArray num element and say, let's start at 0 and we stop at, well, let's make this very general. So I add one more node, the array size node. This guy returns us the size of the incoming array, and the for loop then goes exactly from 0 to the size of the array with a step size of 1. So this should print out on the whole array, and it's kind of different to the first example because we really count through all the elements of the array and print them out separately. So I would expect now a list of message prints. Let's press play, and as you might see here, exactly that is happening. This is how to use the for loop for the array accessing. I would like to demonstrate one more simple thing which would be quite helpful within debugging. And let me create an array resize node. This node does exactly what the name suggests. It's resizing the array to a given input size. Connect the incoming array to these three guys, and let's say the first one we resize to 0, so that element will contain not a single element. This one we resize to 1, so this array will contain exactly 1, and this one, let's say 5, and finally an evaluator node. We add some inputs here. For the sake of clearness, I remove that old guys over here. And so here we go. So if I press play now, we cannot see anything but internally. And this is what I would like to show you for debugging purposes. With a right click on the pin, we see the sizes of the output array. This is size 0, like expected. This is size 1. And this is size 5. What I'd like to show, I don't know if it's very visible within the video codec, but there are different saturations for the different sizes of array. So this guy here gets basically no saturation, a size of 0, slightly more saturation, size of 1, and for every size it's bigger than 1, we got the full saturation. This will be quite helpful while debugging. You will for sure run into problems. Sometimes you get an array of weird sizes, size of 0, you don't know why. But the color encoding here is a good visualization of what's going on internally, and then you might get a hint where your programming problems are located. So this just as a side note. So maybe it's good to demonstrate one more complex example. So let me create here circle emitter. I got an emitter here. Let's add a daemon, like a gravity daemon, connect them. So we got a basic circle emitter in the gravity field. What I would like to demonstrate now is how to access the particles which are contained in the circle emitter. Basically, they are an array when I access them. And finally, I would like to demonstrate how to access certain elements which fulfill a condition and remove these elements from the array of particles. I think this might be quite helpful in practice because you always get some particles which do not exactly what you expect, and I would like to remove them from the scene, so this might be quite helpful as well. Let's get started. So first I get an emitter. The emitter, to make life easier, I take the get all standard emitters, which returns an array of all emitters within the scene. As you might see here, we just have the circle emitter, so this will return us the node of the circle emitter. Well, a node is a very general data type, and we want to have some particles. We know there are particles inside the emitter, so we get a get particle node, connect it, and get out the particle object. To access the positions of all particles, for example, we get the particle channel node. I can show you here in the help maybe. This node returns different channels of the particles. For example, we got the position, velocity, or ID. These are the parameters we can access with this node. Well, at the moment I'm interested in the positions of the particles, so I put in here just position. This guy returns then an array of all the particles contained actually in the scene. So finally, to set the particle positions, we get the node set channel, and it's working exactly like the get channel. We put in the particle object, and for the name we put in position to set a position. So if we connect that to an evaluator and press play, first maybe we start the simulation here, and maybe we change the type of particles to dump particles. If we press play, nothing happens. Why? Well, what we do here is very simple and basically is do nothing. We get the particle get channel positions of all particles, which is in this case vector 3, the position, in an array of 899 elements. Let's check the scene, and we see here we have exactly 899 particles within the scene. So far correct. Afterwards we set the particle positions with exactly the same positions we before get here. So basically we set exactly the same position, and this is why nothing is happening here. So maybe it would be interesting to do something with the position, so the example gets more fancy. So let's do some rotation. Just make a basic rotation, global coordinates. According to map, this is a multiplication of the position with a rotation matrix. Create here a rotation around a diagonal, let's say 3 degrees, and for the sake of stability I put in the steps post here, know that body here, and we connect the rotational positions with the set channel. So if I go back to the scene and press play now, you see the particles are rotated. And since I put the graph within the simulation flow in this steps post here, this is my graph. This graph is executed for every simulation step. So let's see what's happening in the simulation. Well, after every simulation step we got slight rotation, which result in kind of a spiralish simulation flow. All done with this simple node. We can check the array sizes here, for example. We still got all our simulation particle positions here as a vector and set them here. For the following step, I would like to demonstrate how to get particles with a certain, which fulfill a certain condition. So, for example, let's say we want to delete all particles below a certain threshold. Let me create a simple plane to demonstrate visually the threshold. Let's say we want to destroy the particles below -3. Let's render the plane. So, view from the side, we want exactly delete particles below that plane. Just using arrays. I will not use any for loop or any if condition. So now it's getting kind of interesting. So delete particles below that y coordinate. We first need for sure the y coordinate of the actual particles. So I create a vector to components node, and let's clean up the graph slightly and connect the positions of the particle to that node. So this node gives us the x, y, and z coordinates separately. To destroy particles below -3, we said, we have to compare the position against -3, which I put in here. And for the comparison itself, we have the filter nodes. Take the condition filter less than. So basically, if the y coordinate of the particle's position is less than this -3 here, then we want to destroy the particle. So now it's getting interesting. What this condition filter by node does is he takes the input array, compares it to the value, and returns a mask. What is a mask? This is an important concept. A mask basically is also an array just containing zeros and ones. You can see it as a Boolean if you're coming from a programming language. And we can combine that mask with an array that the resulting array only contains that elements of the incoming array where the mask is set to 1. I've tried to demonstrate it here. So we got the second, third, and fifth element set to 1. So at the end we exactly get the 2, 3, and the 5. And this is very important, and we need that to get now that particles below the plane's surface. So let me construct the remove particles node. We got 2 of them. Particle remove all. Well, that's not exactly what we want to do. Particle remove by ID. Well, this means we need the ID to remove certain particles. On the other hand, here we got a mask of the positions of the particles which fulfill our condition. So what we do now is we use that mask and combine that with the IDs of the oncoming array. This node returns us the position, but if I create the same channel like I showed before and connect it here, but this time I don't put in the position, I put in the ID. This will give me an array of all IDs of the particles which are contained within the scene. So I use that mask to combine it with IDs, and this results in all the particle IDs which fulfill the condition which we want to remove. And to do so, I use the filter by mask node. And this is very similar to the if condition in a programming language. I use the mask for all the particles which fulfill the condition and combine that with the IDs, as you can see here, of the particles. And this should result in all the particles which fulfill the condition. I delete them. Additionally, I need at that point the particle node, and finally connect that to an evaluator. So let's clean up the graph slightly, maybe like this. It's looking better. So we got two parts. First part, the first part of the tutorial where we did the rotation here. The second part is basically that part where we tried to get the particles below -3. The y coordinate is -3. We filter that, get a mask of all the particles which fulfill the conditions. There the mask is set to 1. We use that mask to filter the IDs of the particles, and finally use that ID to remove the particles over here. So let's see what's happening. Set the graph and press play. So far the rotation is done, and as you might see, there are no particles below the surface. All right. And this is a very efficient way. And what I'd like to point out again, that there's basically kind of a for loop and kind of an if condition within this graph node. I can show you here. Once again, within the channels, if I press right click on the pin, I see there are 805 channels. This is the ID. So at the moment we've got 805 particles. The same should be in the position array, but these are 805 vectors, meaning the positions. This condition filterless, let me repeat, is filtering the positions according to the y coordinate, which is below -3. We use the mask to filter the IDs of the particles, which we finally will remove. So you can see this part of the graph as kind of an if condition, and the whole concept of working on arrays is a for loop, because every node here works on the whole array size. So the for loop is kind of included in every node, because you're working on the whole array which comes in. All right. So at the end of this tutorial, I would like to say one more thing. I already mentioned it, that one of the main benefits of graph nodes is the multi-threading. And let me create a very simple scene with arrays to demonstrate how the graph node execution performance can benefit from the multi-threading. So this time I just create a constant array num constant, this one. I put in a vector 3, let's say a diagonal vector over here, connect that to the constant, and I want to create a really big one, let's say something like 99 million plus. And for all these vectors we do the normalization. Okay, connect that to the evaluator. And I press once play. As you see, what we have here, right click on the pin, we got a vector of size 1. The array num constant creates a big array, copying basically to each element of the array the same. We see here a big array of vectors, which comes here, and finally we got the big array normalized. All right. So let me change the view. I go into the simulation options. Oh, I just see I did the whole tutorial with one thread. So I use max threads. Now 16 curves are evaluated. And let's say we execute this simple normalization graph of a big amount of numbers or vectors, let's say for 10 frames. Or maybe it would be beneficial if we deactivate the simulation of the particle system to get the full performance for this simple normalization graph. All right, so I press reset, press simulate, and as you might see here, the time of the whole execution is for 10 frames, approximately 7 seconds, with all threads enabled. The only thing I do now is I set the thread number to 1. So we're basically using just single core. We got 7 seconds with multi-threading. Press simulate and keep care of the time. The whole execution takes much longer. Well, most of the nodes are multi-threaded within the GraphNode system, and depending on your GraphNode system, I found it strongly depends on the kind of graph, but normally on a quad-core hyperthreading, I normally get a performance boost between 1.5 and 3 within the execution of the GraphNode system. And as you might see here, we got 28 seconds on a single core execution, though this is a speed improvement factor 4, which looks quite good, I guess. So thank you very much.